friends. In this video, we are going to work with the following concepts. The first is finite sets, then countable sets and uncountable sets. All these concepts are already being introduced to you in your undergraduate course, but still, because these are very much important and necessary for our further course, we are going to recall all the concepts and the corresponding results. So, let us get into the first idea, that is the idea of finite sets. We all know what is a finite set, but when it comes to definition, it becomes little clumsy or difficult to understand the definition. So, let us ask a question first, that what do we mean by a counting? So, when we say counting, for example, let us take a case that when we ask a student to count the number of students in a classroom. What that student basically does is, the student starts pointing out one student that is present in the classroom and starts counting or assigning the number to each student one by one, usually starting from 1. So, 1, 2, 3 and so on. So, this is what the process that starts. So, in short, what the student does is, it is nothing but the assigning exactly one natural number starting from 1 to 3 and so on to each student. So, I am putting an emphasis on two main words, that is exactly one number to each student. Now, let us understand what is this process mathematically means. So, it is nothing but forming a one-to-one map from set of students present in the classroom to the set of natural numbers. I am talking about one-to-one map or injective map from set of students to the set of natural numbers. Now, to be very precise, let us get into the definition. The definition of finite set is, a set A is said to be finite if either it is empty or there is a bijection f from set A to n suffix n for some n belongs to naturals. Now, what is this n suffix n, by the way? It is nothing but the set of first n natural numbers, that is 1, 2, 3, so on up to n. In the former case, that is when A is empty, it is declared that A has cardinality 0, and in the latter case, we say that A has cardinality n. That is, when you have a function which is a bijection from A to nn, we say that the set has cardinality n. Let us work out some examples. So, let us take first set that we have already seen in our set theory video, that is a set of vowels A, E, I, O, U. Question is it a finite set? And we all know that it is a finite set, but now can you prove it? Then the answer is yes, because I just have to find out a bijection from set A to some subset of naturals which is nn. Can you guess what that nn is? Yes, correct, it is nothing but the nn, that is n5. So, there is a bijection from my set A to the subset of natural numbers which is set of first 5 natural numbers, that is n5. Now, let us recall quickly the results that we already have seen at our undergraduate level. The first and the important result is, if you have two natural numbers m and n with m less than n, then there cannot exist any one-one map from nn to nm. Now, intuitively it should be clear, because my domain has got more number of elements than the codomain, and hence there cannot be a one-one map, because one-one means each element in the domain should have different image, which is not possible because in the codomain there are less number of elements. But this result can be precisely proved, and I am sure you must have done it at your undergraduate level. Let us go for the another result, that is, if you have a function from nm to nn which is a bijection, then we must have m and n to be equal. In fact, this is the result which confirms that the cardinality of a set is well defined. Let me go to the next result, that is, if I have a function from A to nn which is 1, 1, and in that case we can declare A is finite and the cardinality of A has to be less or equal to n. Let us move to another one, that is in terms of, for the subsets of a finite set. if I have a set finite and I have another subset, that is B is a subset of A, then one can declare that B must be finite and number of elements in B has to be less or equal to the number of elements in A. Let us have two more very important results, that is, if I have set X finite and if I have a function from X to X, then the following are equivalent. First, f is a bijection, second, f is 1 or injective, and the third is f is onto. So, interestingly, for a finite set, so if you are dealing with function from a finite set to itself, then it is sufficient to prove that it is 1 or it is surjective to declare that it is a bijection. Let us go to the next interesting result, that is, if I have two finite sets A and B and I have a function from A to B, then we have the following statements, that is, if f is 1 then domain has less number of elements than the codomain. If f is onto, domain can should be having more or equal number of elements than the codomain, and if you have two functions, one from A to B and the other from B to A, such that both are 1, then the elements in both the sets A as well as B must be, a number of elements must be equal, and in such case f and g are going to be bijections. So, these are some very important results about finite sets. Now, let us get into the next notion, that is infinite sets. Let us look at the definition of infinite set. A set is said to be infinite if it is not finite. Now, obviously, you must have come across a lot of infinite sets at your undergraduate level, and so I am sure that you know many examples of infinite sets. But I am going to choose two interesting examples to discuss or understand the concept of infinite sets. So, let me take two examples. The first example is I am taking the set of even natural numbers, that is, it is written as a equal to 2n where n belongs to naturals, and the another set I am taking is a closed interval 0 to 1, that is all the real numbers which are lying between 0 and 1. Now, let us ask certain questions. By the way, first of all, do you realize that both are infinite sets? Yes, they are infinite sets. Now, the question is, can you find some difference between the infiniteness of these two sets? Let us understand the question by actually working with the sets. So, look at set A equal to 2n. Now, if I ask you, or rather if I give you one element of this set, will you be able to tell me what is the next so called next element in that set? Then the the answer is yes. That is, if I take say a number 6 in my set A, the next number obviously one can give is 8. Like that, I can, if I give any number from my set, you can definitely give me or tell me what is the next number after that. In other words, I am asking whether is it possible to count the members of this set A. Realize that counting the members is possible, although the process of counting won't end. What is happening? So, let us understand this in terms of mathematical language. That is, one can say it is possible to set up a bijection between set A and the set of natural numbers. What should be that bijection? Again, it is very easy to guess. Let us look at a function f from a to n defined as f of 2k is equal to k. I am leaving it to you to check that this is a bijective function. Whenever such function exists from a given set A to set of naturals, such set is declared as a countably infinite set. Okay. Let us have some more understanding of it by asking a question that can we repeat this same procedure with the other set, that is set B, which is closed interval 0 to 1. So, let us have a look at set B. This set B, so let us take one member of set B, say for example 0 belongs to B. Question is same, can you tell me what is the next real number after 0 in your set B? The problem is you can't tell me what is the next number after 0 in my set B because I am asking about real numbers. Now, this intuitively one can feel that it is not possible to suggest or tell what is the next real number after 0. Now, let us again come back to mathematical description, that is, we cannot basically think about counting the elements of 0 to 1, interval 0 to 1, and hence there can't be a bijection from closed 0 1 to naturals. Let me note here that we are talking about understanding the concept, and of course, we are going to prove this more precisely in coming session. So, let me move to the definition basically. So, such a set from which there is no bijection from a two set of naturals, such set we are going to call it as uncountable set. But as I said, this discussion has ambiguity. So, let us have a precise definition as follows. The first definition in fact is countably infinite, that is, we say a set is countably infinite if there is a bijection from set A to naturals. The second definition, we say a set A is to be countable if either the set is finite or it is countably infinite. And lastly, a set which is not countable is called as an uncountable set. Okay. So, let us go through certain examples to understand these concepts more precisely. So, let us look at the notations that we can develop for countable sets. So, let us take a set which is countably infinite set, and suppose I have some function say f from naturals to a, which is a bijection. Then what we can denote is, let us take any natural number k, and we already know f of k is in a. This f of k we can denote by some notation as a suffix k, and in that sense my set A can be denoted as ak, where k belongs to naturals. So, this is a notation that one can have, and now let us get into certain examples. The first example is set of naturals, which is the obvious example one can start with, and certainly it is very obvious to discuss what is the bijective function that one can have. Yes, I will take identity function I from a to n, and that is definitely a bijective map. We already have discussed this in our earlier video. Hence, naturals is definitely a countably infinite set. Let us have some more good examples. What about z? Yes, z is also countably infinite, and it can again be proved little precisely as follows. So, I will just disclose a map which is a bijection from z to n. It is defined as f of n is equal to 2n if n is positive, and it is minus 2n plus 1 if n is less or equal to 0. Basically, what this map is, it is working as follows. It transfers or maps all the positive integers to even natural numbers and all the negative integers to the odd natural numbers. Okay. So, I am leaving it to you to check that f is a bijection. Now, let me move to the next example, which is again an interesting example, that is n cross n. You see, n cross n is also going to be countably infinite, but proving it is countably infinite is going to take little time. That is, so first of all, let us visualize what should be n cross n. If you you can see in the diagram that n cross n can be plotted, the elements of n cross n can be plotted in R2 as dots 1, 1, 1, 2, 1, 3 and so on. So, in general m comma n can be plotted in R2, and we can imagine n cross n as a subset of R2. So, what we do is we define a function that maps the elements of n cross n to another subset of n cross n, that is A, which you can see in the diagram. This function is given by f of x comma y is equal to x plus y minus 1 comma y. Now, once I get A, we can actually find out another function which will map A or every element of A to the set of natural numbers as follows. You can see that I can count the members of A as this is first, second, third, 4th, 5th, 6th and so on. We define a function g from set A to set of natural numbers as follows. It is g of x comma y is equal to 1 by 2 times x into x minus 1 plus y. Neglecting the expression, let us understand what this function is doing. This function in fact is counting or rather mapping the points to naturals as follows. This point will be mapped on to 1. This point is actually 1 comma 1. It will be mapped on to 1. This is 2 comma 1 which will be mapped on to 2. Then 3, 4, 5, 6, 7, 8, 9, 10 and so on. So this is how it is going to get or give us a bijection from set A to set of natural numbers. Hence we have a map which is going to declare that n cross n is countably infinite. Now let us move to the next set, that is q plus. Q plus is the set of all positive rational numbers. What is your guess? Can I declare that it is countable set or countably infinite set? The answer is yes, it is countably infinite, and a simple function is going to in fact declare that q plus is countable because the background work we already have done. Let's see what that function is. So if you take any rational number, can you see that it is lying inside a set n cross n? Yes, it is going to lie in the set n cross n, and so using this fact, let us find out a function f from n cross n to q plus as f of m comma n is equal to m upon n. One can now prove that this function is onto, and one can use the following result which will declare that q plus is countably infinite. The result is as follows. If I have a function f from a to b where a is countably infinite set and the function is onto, then one can say set b is also countably infinite. Hence q plus is countably infinite. In fact, on similar lines one can prove q minus, that is set of all negative rational numbers, is countably infinite, and thus set q becomes countable or mainly countably infinite set. Now let us move to the next important example which we have just discussed but never proved, that is set close 0 to 1. We want to show that this is an uncountable set, and we will be proving it by method of contradiction. So suppose possible a is not uncountable set, that is, let us take my set A as ak, k belongs to naturals. Now let us observe one point, that any number between 0 and 1, any real number between 0 and 1 can be expressed in decimal form as follows. So can you see that ak for any k can be written as 0 point, ak1, ak2, ak3 and so on, where what are these akis? They are the digits between 0 to 9. So every member of my set A can be represented in decimal form like this. Now what we are going to do is we are going to consider or rather construct a new real number, say y is equal to 0 point b1, b2, b3 and so on, where bi, ith digit after the decimal point is not matching or it is not equal to aii. Okay, so this is how we are constructing it. So this makes this number y different from each element ak, because for any k the corresponding ak have got a digit akk, but the corresponding digit in y is bk, which is going to be different from akk. Hence this number y belongs to 0 1, but it is not equal to ak for any k. Hence this is creating a contradiction, because one side we are saying y belongs to a and we are saying y is not equal to anybody in set A. Hence there is a contradiction, and this declares that the set is uncountable. Now once we prove closed 01 is uncountable. Since closed 01 is a subset of R, in fact this suggests that set of real numbers is an uncountable set. Thus, in this video what we have learned is the set of the concept of finite sets, countable sets and uncountable sets with several examples. Thank you.